Good morning, everyone. We are going to get started with our breakout sessions. This is winter production in a geothermal heated high tunnel with Eric Jellum. Eric received a SARE Farmer Rancher grant to test this out, so we're excited to hear about his project today. Eric began farming in 1998 after moving to Iowa from Washington State, where he worked for years for Washington State University at an agricultural research station. During that time, he got his master's in soil science from Washington State University, and he currently farms in north central Iowa with his brother. Please join me in welcoming Eric.
Well, thank you, Krista, and I'm sure you're all glad you got reservations to come to this. Before I get started, I should throw out a thank you to SARE, because I've had several SARE grants over the years, and for farmers, that's about the only thing available. If you have a project you'd like to pursue, that gives you a chance to do it, and I've really been appreciative of that. So to get started here, before talking about the project, I want to just do a little primer of geothermal energy. May have gone the wrong way. There we go. I'm going to use data from Nashua, Iowa, because in the soil moisture network that is all over the state of Iowa, that's the closest station to us that has continuously recorded environmental data like soil temperatures. So the 50-inch soil temperatures that I'll refer to as we go through this come from Nashua. If I talk about 8-foot soil temperatures, they're my own data from the 8-foot deep loop for a dryer project that preceded this project. 15-foot depths I'll refer to. That's mainly discussion from geothermal installers and system designers. So this graph here is long-term average air temperature and just a 3-year average of 50-inch soil temperature. I used long-term average air temperature because in order to keep from having a graph that gives you vertigo, you've got to do some averaging to have a nice smooth curve for air temperature. So this is, I think, a 30-year average and then averaged by month. And I did that just to make some points about geothermal energy. So you can see the darker curve that doesn't have quite the amplitude of the oscillation is the soil temperature at 50 inches at Nashua. And the thing that I should point out, besides the decreased amplitude, is it's got a peak that is shifted later than the air temperature. And the deeper in the soil profile you go, the greater that shift will be. So it shifts later, and the amplitude of the oscillation is attenuated, or it decreases. So at 50 inches, the difference between the high temperature and the low temperature 6 months later is about 30 degrees. If you go down to 8 feet, it'll be about 20 degrees. And then if you go down to 15 feet, it shifts later yet, and the peak, rather than occurring in July like the air temperature peak, it'll occur about the beginning of November, which corresponds to the beginning of heating season. So the amplitude at that time, then at 15 feet, will be only 5 or 6 degrees above the average temperature, and then 6 months later, 5 or 6 degrees below. So because that shift to the beginning of the heating season and then the small decrease in temperature as you go into the winter, that's become sort of a favored industry standard for placement of the geothermal lines at that depth then. And with the use of directional boring machines, that becomes more practical. So there's less pit digging and more boring to place these geothermal lines. If you focus, rather than on the whole year, just on the November, December, January, February, and March, that's the winter portion of the year, and you look at the average daily temperature rather than the averaging that I did before, it gets awfully busy. And if you want to look at what the low temperature would be rather than the average daily temperature, if you just use your imagination to shift all these lines about 10 degrees colder, that'll be a good snapshot of what the average low temperature is. And so you can see how much variability there is from not only year to year, but day to day. And yet, if you were to look at the same 3 years and look at the soil temperature, it smooths out pretty dramatically. I mean, there's a lot of thermal storage capacity in the soil, and that's evident in how little busyness there is to the temperature graphs. So it's reasonable to just average a few years and figure that year in and year out, that's about what the soil temperature is going to be at that depth. So that's what I've done here. And if you notice that at the 50-inch depth, from the beginning of November to the end of March, that temperature is slowly decreasing. And if you had a line for 8 foot, it would be parallel and a little bit above that, but up around 50 degrees there. In Nashua, probably 49 degrees. If you went down to 30 feet, it would be constant. And so during the winter, it would give you a little bit higher temperature, and the delta T is very important here. So at 30 feet, normally, wherever you go, that temperature is going to be constant throughout the year. It's also going to be what the well water temperature is. So open loop geothermal systems for homes are popular if you've got the water quality to do that. Because you've got that constant temperature and they operate more efficiently. A closed loop system early in the winter can be more efficient, but during the middle of winter and late in the winter and early spring, an open loop, because of its constant temperature, will be more efficient. So that being said, if we move into a geothermal system and just describe it a little bit, I want to loosen up the linkage between the ground loop and the heat pump. Typically, when we think of geothermal heating, we think of a heat pump with a ground loop. So we have a ground source of energy, and this is we just got a new heat pump last year because the one that we'd had for 24 years finally gave up. And so the heat pump, because of its refrigeration cycle, can make use of this low temperature ground heat. That's the beauty of it. A heat pump nowadays typically would have a coefficient of performance of 4. And what that means is that 1/4 of the heat produced would be from operating the heat pump and the other electrical components related to it. And then 3/4 come from the ground. So the circulating water through the geothermal lines is a very low input, low energy input, and very inexpensive to do. Operating the heat pump itself is expensive. It's an electrical contraption. So if you didn't have the geothermal lines in there and just operated the heat pump, you wouldn't get any more than you would having toasters or hair dryers there. The beauty of the heat pump is that refrigeration cycle then that can take advantage of the geothermal lines. So if you have applications that you don't have to worry about people's comfort level, the geothermal portion of it is something that could be used alone. And if you don't have to have the expense of the heat pumps are quite expensive. If you don't have to worry about the expense, and the operation of the heat pump is expensive as well, then you could have a system that might up front be pretty expensive to install, but then you'd have years of very inexpensive heat. So I don't want to rule out the heat pump because that may be one of the applications that you use the geothermal heat for, but if you can get along without it, then all the better. So having that geothermal heat available, if you have applications that don't require a very high temperature, what might that be? I mean, my first project with geothermal was to dry corn, which might take a little bit of work to get your mind around because it's low temperature. But for small farmers or farmers that have bins that don't have very deep grain columns, natural air drying is a pretty competitive way to dry corn. Competitive with high temperature, high capacity gas dryers that can get up to 200, 220 degrees. Natural air drying just pushes a large volume of air through the grain and lets the drying capacity of the ambient air do the work. So for a limited time in the fall, a month to 6 weeks, that's the normal natural air drying season. But it's also the case that if you cut the airflow rate in half, you can do it for about 20% of the fan horsepower. And so cutting the airflow rate in half and running the fan twice as long, you can drive for about 40% of the fan cost. If you do that again, it gets down to about 16% of the fan cost, the operating cost. And the only way that you can do that is by heating the air, because the air during the winter deteriorates for drying corn so that you couldn't get the corn drier than 18 or 19% without heating it. And if you heat it with LP or propane, you take away most of the advantage of drying slowly over the winter. But if you use a low temperature, inexpensively acquired source of heat like geothermal, then that becomes practical again. So my first project was to do that, just dig in a geothermal line, and in this case, it was down to 8 feet. It was an 800-foot trench, 8 feet deep, with 3 3/4-inch geothermal lines at the bottom. And they went out in a trench for 400 feet and emerged into the greenhouse on our house where I could have a flow meter and temperature ports and a place to add in ingredients and let any expansion that needed to take place happen in a protected environment. We have a little greenhouse attached to our house. So then back into the ground, pumped by a very small pump, and back to the dryer where it went through a heat exchanger in the drying air stream. So, I mean, the pump here is a 3-speed pump. On low, it uses only 60 watts, and on high, it's 87 watts. So not a very big pump to circulate that water and get enough heat to dry 3,000 bushels of corn. So you operate that all winter, and it's not a very big investment. I mean, the fan costs more, and your fan size is pretty dramatically reduced. And so for 6 years now, we've done this. This has been a pilot project, and it's been quite successful. So I was tickled with the results from that, and I started looking at greenhouse heating and kind of took that up as a challenge, although I'm not a vegetable grower. So I have a neighbor who is a vegetable grower. Steve Strasheim is owner of Twisted River Farm, which is just 7 miles north of us. And I approached him to see what his interest was in collaborating on a project. And he's progressive, he likes new ideas, and so he was pretty quick to take me up on it. And so I put up a high tunnel on our farm, and he was the producer in a project that we got another SARE grant for. And so he designed some trials with different vegetables, different varieties of lettuce and spinach and kale and onions, and he had broccolini. It's the first time I'd ever heard of broccolini, but he just tried a scattering of different vegetables there. So my part of the project was to design the heating system and take the numbers on it, take temperatures, and see what its performance was. And his was to be the grower and assess what the value of doing this was. And for him as a producer, he had a high tunnel just like the one I put up. And high tunnels, they extend the season and they make the primary season warmer, but eventually you get lethal temperatures. And so having a heat source that was inexpensive to keep the vegetables from freezing, had value to him. And for anybody else interested, they have to decide what the value is to them, but my challenge was to keep a temperature that was not lethal. And as far as he was concerned, that was about 20 degrees. And, spinach is tougher than I knew it was. I mean, it'll take colder than that. Lettuce, probably the threshold there is about 20 degrees. So designing the system for the greenhouse had different considerations than for the dryer loop that I use for drying corn. For one thing, as you can look back at the graph that we saw to begin with here, during the winter months, that soil temperature is dropping and it's bottoming out at 50 inches kind of in the heart of the winter. So you're down about 35, 36 degrees at 50 inches. That's in Nashua. We'd be about a degree colder up in Osage. But at the same time, if you look at the solar availability, that's bottoming out about the solstice, the winter solstice in December, and then in January, February, it's increasing and starting to increase pretty dramatically. So trying to make use of that solar energy and combine it with the thermal storage capacity of the soil in there, even though it was not a huge volume of soil, if you could replenish that heat in the soil by capturing some of that that solar energy and storing it in the soil on a daily basis or whenever the sun was out. You go into a greenhouse, even without a heating system, in a January day that might be 10 degrees outside, you could have short sleeves on in the greenhouse. So there's available energy there to put away. So to put these side by side, the soil temperature graph on the left is at 8 foot. That's off of my dryer loop, and that's from this year's data. And then I just isolated the winter months for the solar radiation just to illustrate that combination of soil stored solar energy and actively collected. And so that seemed like the logical way to design a system for the greenhouse, is just to put it entirely beneath the footprint of the greenhouse. So we went about doing that. I hired a guy with a trencher that would trench down 5 to 6 feet, and he trenched. I put an inner loop and an outer loop, and then the very outer loop is just the perimeter of the greenhouse. You can kind of see the pink board sticking up. If I had a pointer here, I could point it out, but I think it's pretty easy to see that I put a 4 foot deep, 2 inch thick pink board perimeter around the whole greenhouse. And then the geothermal lines are in a vertical slinky. So it's a narrow trench that I could just drop that coil in and just pull it along in about a 1-to-6 ratio. So for every foot that you went, you had about 6 feet of geothermal line in the loop. And so the inner and the outer loop were separated by about 7.5 feet, because this greenhouse was 30 feet wide by 54 long. So they were evenly spaced. And then I backfilled those to the top of the slinky and laid a drip irrigation tape on top of that so I could keep the soil wet. And that improves the thermal storage capacity and the conductivity quite a bit. So I thought that was quite important to do that. And then backfilled it and erected the high tunnel. So at the other end of where this picture was taken from, the building that this is all attached to had a nice wall that I could arrange all the plumbing on. And the idea of the project was to reverse the flow daily, so that when you're putting heat into the ground, you would have one flow direction. And then at night, when you're extracting heat, you'd reverse the flow so that the water coming out of the ground would be a little bit warmer and maybe operate a little more efficiently. Doing that required quite a few valves and fittings, and there's electronic solenoid valves, and you can see the flow meter and the pump, and it just gets to be kind of a busy wall. On the right there, is a 4-inch diameter PVC pipe. That's just an expansion tank substitute, and it's a place where you can add ingredients. So got it all set up, had 2 heat exchangers. I think they're 2 foot by 2 foot heat exchangers, 3-row, and started the system going and got very disappointing flow rates. And so this is the portion of this where I have to make confession that with this few people, I don't see any priests in here, so I'll just have to confess to myself. But I did make some mistakes here that were errors in judgment or just mishaps. One of them is that the geothermal line, which is the black line in my hand there, has an inner diameter that is quite a bit more than a 3/4 inch PEX line. And then the brass fitting is a 3/4 inch PEX fitting, which goes inside the PEX line. The geothermal lines are butt fused, and so there's adapters or fittings that go over the outside of the geothermal line. And so that the geothermal line is technically 3/4 inch, but it's closer to 7/8. And then when you put a fitting on that, you're fusing a fitting on the outside of that, so you're not occluding the flow. And so it being already a bigger diameter, I realized I should have stepped up a size when I came off the geothermal. They came out of the line, and all the other fittings on that wall were black poly, some PVC. It would be the same diameter. I happened to be holding PEX, which I didn't use, and I could just as well be using holding PVC or the black poly. They're thick-walled. The inside diameter is less than 3/4 inch for a 3/4 inch fitting. I hadn't really considered that. So the fittings on the wall were replaceable. I mean, I didn't have to do any digging, so I upsized some of the fittings. If you manifold 3, and in this case it was just 2, but if, like in the dryer loop, 3 3/4 inch lines, if you manifold them together, you should step up to 1.25 inches. If you're using poly fittings at that point, I would say 1.5 inches to get the same kind of diameter that you would with the geothermal fittings. So that, it's something to take note of. I don't think it was a serious problem. What it ended up being mostly, well, 2 factors. The outer loop, which was the longer of the two. The inner loop is 600 feet, the outer loop is 700 feet. I never could get the flow that I needed out of that. I could put a PTO pump on a tractor and put enough pressure to practically blow the system up, and I could get pretty good flow out of it. But then when I took it off of that and just put the circulating pump on, it was some fraction of 1 gallon per minute. So that I'm calling a kink for, I guess, because I think it's most likely to be that. It could be occluded with something in the line. Whatever it is, it wasn't working. I tried to bypass a corner, because when you drop that vertical slinky and you come to a corner, you've really got to round that corner off to keep from bending that geothermal line beyond a radius that it should be bent. And I suspect that that's probably where a kink might have occurred in the backfilling process. If I had, well, I thought about it quite a while afterwards, but had I simply flipped that coil over so that each loop came off the one before it with a connection on top, then I could have bypassed that corner with just a little bit of digging and made a nice radiused curve and probably avoided that problem. But live and learn. So the other problem that I kicked myself for not thinking of, because it was fairly obvious once it occurred to me, is that drip irrigation tape, once you put 18 inches to 2 feet of soil on top of it, you smash it down pretty good. And so it drips reasonably well for about 10 or 15 feet, but not for the 150 feet or so that I needed in there. So I didn't have any means of keeping that soil wet, and without any rainfall in there, I mean, where the irrigation was just enough for the crops, I didn't want to be doing my drip irrigation from the surface, because I would be leaching nutrients out of the primary root zone. So not being able to use the drip line that I put in just above the slinky, I just didn't do it. I mean, I could go in yet and put in drip irrigation line above the slinky, but since we started this project, there's been continuous crop production year-round, so it's a little hard to find a time to do that. So some of these problems are soluble. I guess maybe all of them are soluble with enough enough time and money to throw at it. So collecting all that and thinking about it, I think, what else could go wrong? We got started, Steve got crops planted in there, and then Mother Nature answered the problem, what else could go wrong? We had a derecho a couple of years ago, probably affected some of you in here. 17th of December, it seemed like it was. Affected quite a bit of Iowa and Minnesota. But it came through and did its dirt in about 30 seconds and then moved on. So this is what I came out to after I came out of the basement. Because I went down in the basement, and about the time I got to the bottom, it went quiet again. I mean, it sounded like a freight train coming through when I went, but it just came and went in a hurry. And what it had done to the greenhouse is torn a hunk of the barn wall by the tractor there, thrown it up over the hay bine, up over the hood of the grain truck, behind the red grain truck, 150 feet without hitting the ground, and just inserted itself nicely into the greenhouse. About 2 months after we put the skin on the greenhouse, and before I got it added to our insurance policy. So that was a big problem too. And it happened, fortunately, to be a warm wind, and the next day was pretty warm too. It blew all night, and so it tattered that plastic, kept ripping it all night. And the next day was warm, but with cold weather coming that night. So fortunately, we had, a number of good neighbors come over, and we sewed a couple tarps together and pulled them up over to keep the cold out when it came that night. But it was a problem. It shaded a lot of the greenhouse, and when that wind would come down the skin of the greenhouse, it would find its way underneath that black tarp. You could not make it very tight. So about the latter part of January, we had a warm enough day, pretty brief day. It was a race to get it on, but we seamed in another piece of plastic and made it usable again. So the first year's data is kind of a bust. I'm not going to bother showing you any data from that. I'll show you this, which we saw earlier, but what's happening here is that trencher looks like it's going off of the footprint of the greenhouse. It is. It's going over to the bin behind, which is the 3,000 bushel bin that was my dryer project. So there's an 800-foot, 8-foot deep dryer loop for that dryer project that is only 50 feet from the end of the greenhouse. So I put that in just thinking it might come in handy. As long as you got a trencher out there, you might as well. It's not all that much extra work or geothermal line. It turned out to be very fortunate. So we connected those up, and for the second year of the project, that inner loop in the greenhouse went to one of the heat exchangers. The dryer loop went to the other one. So it was kind of a combination system that at least provided geothermal heat for the greenhouse. This is just a snapshot of what the second year looked like using Nashua data. So it's a 50-inch soil temperature, and then daily temperatures for the winter months there, November through March. So you can see about the end of January, we had the coldest night, and then after that, there really wasn't much challenge to the greenhouse. So looking at the data finally, month by month, this is November. November was not very challenging. The blue line is the outside temperature. We had two recording thermometers. One was in the middle of the greenhouse, just about crop canopy height, and then the other the other thermometer was on the north side in the shade to collect ambient air temperatures. So the blue line is the outside temperature, and the red line is inside. Not much to to show for November. December got to be a little more challenging, but so far we're keeping above our 20-degree threshold. And this is not operating continuously. This is on a thermostat, so it comes and goes as needed. So if you had it run continuously, you could probably keep it warmer, but if you don't have it on a thermostat, you're wasting heat. There's only so much stored in the ground. If you use it when you don't really need it, you're not going to have it for when you do need it. So it's important to have it on a thermostat so you don't squander it. And if you had a higher threshold you were trying to maintain, you'd have to use it higher. But I was aiming for 20 degrees, just like Steve was hoping for. And that's why it gets down to 20 a number of times there, and looks like it's tenuous, and it maybe was at those temperatures, but it's still maintaining the temperature above 20 degrees. January was the coldest, and you see by the end of the month where it drops down below minus 20, the greenhouse temperature got down to between 16 and 17 that night. Still quite a difference from outside temperature, but not quite the threshold. The other thing that I want to point out here is how high those peaks go up during the day. I mean, you get up over 70 degrees, that's way more than you need to. So there you've got capacity to put some of that heat away if you've got enough heat exchanger capacity in the greenhouse. So that's something that needed to be addressed. The other thing that could have been done was to do some means of heat retention at night. So if you had a blanket you could pull across at the bottom of the trusses, you could even rig that up with a garage door opener so it was easy to do on a nightly basis. That would retain a lot more heat in the ground. And so if you put excess solar energy into the ground better than we were able to with those two small heat exchangers, and you retained heat at night, that dropping below 20 degrees on the last day of January probably would not have happened. The other thing is that a high tunnel is really meant for season extension rather than winter production. There are better designs for winter production that most of them have a well-insulated north wall and the glazing is all facing south. That's probably worth considering rather than trying to make a high tunnel design work for this kind of production. So going into the third year, which is this year, I put in another heat exchanger. So we have 3 heat exchangers in series here, and they're all connected to the dryer loop. So I took the inner loop of the greenhouse out of the picture completely. It's all coming off the dryer loops just so it wouldn't be a hybrid system, be a little easier to evaluate. And as it turned out, the dryer loop was doing most of the work anyway. So going beyond the SARE project and not having a budget anymore, my pocketbook started complaining about buying expensive components. So this other heat exchanger is from a salvage yard. It's a radiator out of an F-350 Ford pickup. Not a 3-row design. I mean, originally I had larger 5-row heat exchangers that we took up to Steve's greenhouse when he had a high tunnel before I did, and so just to play around with heating with groundwater, we took them up there, made another little error in judgment, and made sprinklers out of them. So those were out of the picture. Got smaller heat exchangers, but now added this third one in, this radiator. So there's more capacity to put heat away, but with the dryer loop being outside the footprint, there really wasn't a lot of point in putting heat back in the ground when the ambient heating and cooling was controlling most of the temperature fluctuations there. I tried for a while just to see if I noticed a difference. I did not. So the temperature coming out of the ground is a function of what Mother Nature makes it. So the only reason to run the fan during the day is to cool the greenhouse down if need be. And there is a vent that'll open automatically to help cool it down, but there really isn't the same usage that the original design, where you would put away excess solar energy for use at night. I mean, that would have been a good reason to run it during the day. There's not all that much compelling reason to do that. So, hard to see in this picture, but the line at the bottom of the radiator is where the water comes out of the ground and goes into the heat exchangers. There's a temperature port there. The heat exchangers are in series. The last one has a line that goes back into the ground, and there's temperature port there. And so with that, and with the flow meter that you saw in an earlier picture, I can calculate what the heat flux is. So this is the temperature at 8 feet that I'm measuring from our greenhouse on our house, which is midpoint on this 800-foot loop. So on milder nights when the heat doesn't have to run, and there can be some equilibration with the ground temperature around the geothermal lines, I can get an idea of what the ground temperature in general is doing. And through the 2 months that I'm showing here, it's dropped about 10 degrees. And it'll continue to drop until it gets down to about 40 degrees later in the winter. So that's just where we're at with that loop. And then these slides got a little out of order, so I had to skip. This is the last slide I'm going to show you, and I want to take a little bit of time to look at this because there's a lot going on here. The green dots at the top are basically the slide we just looked at. That's the ground temperature without heat extraction. There's 2 snapshots here. This has just been a weird winter. I mean, it's been warm. It hasn't been much challenge to the system. So the 2 nights that I'm showing here are kind of outstanding for what it's been. I mean, what's coming up this week is going to be a good test, but that's this week. It's not available to show you. So on the 28th of November, it got down to -1, and on the 18th of December, it got down to about 9 degrees. So the green dot, the row of green dots, when you're extracting heat, you can see how they drop down a few degrees there. That's at the midpoint in the loop. So the yellow X on the 18th of December, that's the temperature going into the heat exchangers. And so the blue X is the temperature coming out of the heat exchangers. The orange box is the temperature in the greenhouse. And then the triangle there, I can't tell quite what color that is, but that's coming off the fan. So off the fan, it drops the temperature just going through the greenhouse because it's passing over the glazing and cooling off. But from going into the heat exchangers and coming out, there's about 13 degrees difference. And the flow rate I don't show here, but it was about 4.8 gallons per minute. And so you can calculate that that's about 31,000 BTUs per hour. And I didn't have the temperature ports in on the 28th of November, but just projecting from the other temperatures, I'm guessing that was about 38,000 BTUs per hour. So the cost for running the pump was 150 watts. We're paying about a dime per kilowatt hour for electricity, so it's about a penny and a half an hour to run that pump. If you were to get 31,000 or 38,000 BTUs out of a gallon of LP, it would cost you at $1.50 a gallon for LP, it would cost you about 56 cents an hour or 68 cents an hour, respectively. So that's pretty cheap energy. I mean, if you can get by with the low temperature heat that that geothermal is, then you've got a very inexpensive heat source. If you have to use LP, you can see how much more it's going to be. So if you have to have a higher temperature, well, that's what you need to do. But if you can get by with that low temperature, it's very inexpensive. So let's see, I've got. Okay, let me just quickly point out on that line where shows the ground temperature dropping slowly. At this point, it's dropping below the average temperature, which would be the well water temperature. So from here on into the winter and into the spring, that ground temperature is going to continue to drop, but the well water temperature would be constant. There is a device that I just recently became familiar with. A company in San Jose, California has produced and is just hitting the market now. It's a combination of a pump and a heat exchanger that drops down a well. So if you bore two wells and you pump out of one through the heat exchanger and deposit it in the other well, the heat exchanger has another loop then that is goes to the point of use, and in their most likely a heat pump, but in this case it could be a greenhouse, it could be a corn dryer. It's a lot lower cost for installation, and it maintains the constant temperature by using groundwater, so you don't have that temperature dropping through the winter. Something very intriguing to me that I'll no doubt pursue. With that, I think I'll just quit and open it to questions, suggestions, any discussion.
So what was the cost of that project? You trenching, everything to set the system up. What do you think it cost you?
I figured, my brother helps on all these projects. I mean, we farm together, so he gets roped into helping a lot on this. I hired a backhoe to dig the trench for the dryer loop down 8 feet. We laid the lines and did all the plumbing to connect them up. It was cheaper than it would have been if you had that done. I mean, it depends on how much of it you can do yourself, but I figured that probably $5,000 would have done that system for the dryer loop. I had a 3,000 bushel bin that I was drying in. I had more dryer loop than I needed for that. I mean, the last couple of years, after making sprinklers out of my big heat exchangers, I had that radiator from that F-350 Ford as my only heat exchanger in the drying air stream. And that was adequate to raise the temperature 7 to 10 degrees. So you get down to 15% corn with 7 degrees and down to 14% with 10 degrees. The greenhouse loop, cheaper because less length of pipe. The whole grant, I think, was about $6,500, $6,600. And of course, I'm a little shy about asking for too much because I want the grant. And so I end up in each of my projects taking out of pocket, but not terrible. So, probably $4,000 or $5,000 would have done that also. If I had done the plumbing right, if I had it to do over again, I could probably, that's one thing I forgot to mention, is in my desperation to get more flow in the greenhouse, I upped the size of the pump. I bought another pump, and it still wasn't adequate. If I had designed the system, eliminating some of my errors, I could drop that pump size back down, and my operating cost would be a lot less. So, you're right in asking that because the cost of doing this is mainly the upfront cost. Once it's in there, you've got years of low-cost heat available there. But that's why I bring up that device that I mentioned at the last there, because it's a cheaper installation. I mean, boring wells, if you got a fairly shallow water table, $20 to $25 a foot, I think, is what the installer that I visit with periodically would cost to go down, and maybe 60 feet would be enough. Our water table is pretty shallow, but you need a well to drop this device in, and then a well to put it back in, or a tile. And so you've got some boring costs there. You might get up to $10,000 on something like that, but it's got more capacity than either of the systems that I've got. So that device, if I am costing that correctly, that's for a 6-ton heat pump. So it's capable with its design parameters of putting out about 5 tons continuously. So it's pretty capable. It would heat a larger greenhouse. It would dry more corn. That's just the smallest size that they make. They make a 6-ton, a 20-ton, and a 100-ton unit. And they're intriguing because they can cut the installation cost in half, and the operating cost is quite good too. Any other questions?
Eric, I'm wondering if you can talk a little bit about the process to apply for the SARE grant, just so folks have an overview of kind of the application.
Yeah. If you have an idea that you want to pursue, SARE has a period of time that you can submit a proposal, and they also have help if you need it for grant writing. And with the years with the university, I've done enough writing, been involved with enough projects that I haven't made use of that, but it is available. And the proposal then, you flesh it out with all your expected costs and what your expected results are, and it gets reviewed by a committee that I think is made up of producers and university people, maybe some industry people. Imagine that team rotates, but it's got quite a few eyes from quite a few different backgrounds looking at it and evaluating it. I think there's it's been about a 40% funding success in recent years, something like that. And so if you've got a good, strong proposal, you're pretty likely to get funded, depending on how much you ask for. And I haven't pushed that envelope as much as I probably should, because these projects always go over budget. And this project is not something that I'm doing for remuneration. It's more academic curiosity, because I'm not benefiting much from it. But geothermal is something that's become sort of a passion for me, and it's something that I've thought about for years. Now it's becoming more widely known that we need to do something about our use of fossil energy. And if you can do something like this that not only eliminates most of the fossil energy use, but also makes use of solar better, and it's also cheap once you get a system installed, that's sort of the ideal solution. So thinking of applications for low temperature geothermal is kind of an act of the imagination. And there are other things. 2 years ago, I think, I air conditioned our house. I bypassed our heat pump, used the duct system, and I air conditioned the house just with well water. Our well water is cold enough at 48 that it not only could cool the house, but dehumidify it. The further south you go, the more difficult that would be. But it was quite comfortable for us. I've been heating and cooling our garage. Our garage has a floor loop in it that I put in there thinking I would hook it up to a heater at some point. All I've ever used in there is well water. Keeps the snow and ice melted off the car in the winter and keeps it fairly comfortable to go out and do projects. And in the summertime, it keeps it nice and cool. Just run it once in a while when you need to cool it down some. And if it gets too humid, you can run a dehumidifier. Although I could set up a radiator out there to dehumidify also and just use well water for that. So it's maybe $25 a year to do that. And it's a 28 by 30-foot garage. So there's different applications that probably are just waiting to be thought of. And climate-controlled storage, for example.
I read an article recently where there was a similar setup. I didn't read the complete article, but they talked about actually cooling the greenhouse.
Yeah.
In some months.
Yeah.
It might actually be a benefit for certain crops.
Yeah.
Do you think that's a possibility?
Well, absolutely, yeah. And that's the reason to run the fan in the summertime when I'm connected to this big loop that goes outside the footprint would be just to cool it. I've got the side curtain on one side that I can roll up probably 4 feet because I made a little extra tall wall. And then I've got a vent on the end wall that will open up 2 foot by 3 foot, I think is what that vent is. Sometimes that's not enough. And so if you run the fan, you can help cool that off. The north wall of this high tunnel was facing what used to be a nice thick row of old spruce trees or windbreak, and that derecho kind of took care of the problem of having a nice windbreak. We still have some trees there, but it sure thinned it out. But at the time that I put the high tunnel up, there wasn't much even scattered radiation coming in from the north, so I insulated that wall and kind of wished I could have insulated up the roof a ways, but that wasn't as easy. So that north side wall is not something I can roll up. It's just the south and the vent on the end. So it gets to be a little difficult sometimes to keep it cool enough. But usually rolling the sidewall up is enough.
I feel like I really want you to come and evaluate the systems at my house. I know I could do a lot of improvement out there, so thank you. That was a wealth of information.
Well, thank you. Thanks for your interest.